Okay, shall we start? The class before us, these things break down, but they were able to fix it before this class. So there is some kind of uncertainty in the equipment here, but it's been quite reliable. One of the things that we do mention about the probability, there is a little point here. You can think of random variable is sort of like collapsing some of the outcomes into one class. So you would not expect that, whatever a subset in the original sample space, you will be able to find an event in the defined by the random variable. This is the situations here. So this note, I'm glad some of you asked after class. What it says is that the random variable is counting how many heads you have. So as a result, the event that is defined by the random variable would be x equal to 0, or x equal to 1, or x equal to 2, or x equal to 3. So the random variable collapses some of the outcomes into one number, and namely, how many heads are there. But for this is an event in the original sample space because it's just a subset which consists of two outcomes, 3 heads, 2 tails, and 1 head. So I have 2 outcomes here. But then this will not find the right outcomes or the event in the random variable itself because it doesn't correspond to x equal to something or x belongs to something. All right. So suppose you x, because here it would definitely your x will be 1. But then when x equal to 1, you will have to include the other 2 outcomes, which will be HTT and TTH. So these 2 outcomes are missing here. So as a result, you cannot find an equivalent event which is based on the random variable itself. So this is a little bit fine thing, but probably I think here in our module, we probably since the focus is on the random variable itself, so whenever we want to calculate certain probability of the random variable, all we need to do is to pull back into the original experiment, the outcomes, and then calculate there. So usually our motivation is x equal to something or x belong to something. So we will not be, and then calculating the probability is only pulling it back to the original sample space. So these situations is unlikely to happen in our actual calculations. So I think we have done this. And so one way is that we table so 0, 1, 2, 3 are all the possible values of the random variable, all right? And so all we need is to list out this table, and then the second row corresponds to the individual probabilities. We usually call this as the probability mass function of the random variable x. We changed the name a little bit. When we are dealing with continuous random variable, we call it probability density function. But when we are dealing with discrete, we want to emphasize that it is individual masses there. So we call it probability mass functions. But in this lecture notes, sometimes we call it probability function. All right. So the distinction is usually very clear in the context of what we are talking about. So we shouldn't make a big fuss out of it. When a pair of fair dice is tossed, what is the probability that a sum of 3 is obtained? So I think we have done this. And I have mentioned that 7 is, the sum equal to 7 has the highest probability among all the other sum. And it has something that in the design of the Monopoly game, how they establish the charges if your opponent step onto your on your property. So here is basically saying that random variable can be broadly classified as discrete and continuous. There is something a little bit unfortunate here, because the mathematics that we are handling with discrete thing would be basically using summation and subtraction, or either addition or subtractions. And when we are dealing with continuous random variable, we are using integration and differentiation. But if you're thinking of the integration, it's just a way of adding things up, but in a very, abstract version. Actually, Archimedes already used integration, but he add things up, but then let the gap to be very small to find out the area. So in a way, integration parallels to your addition, and then subtraction parallel to your differentiation. So only the notations are different, and then the operation is a little bit different, but there are no big differences. The only annoying thing is that you have to use the right notation for the right thing. This is not entirely 100% correct, but it is correct at this level, because there are some other random variables that are neither discrete nor continuous, but it will not concern us at this point of the in this module. So what do I mean by discrete? It means that X can assume only a finite number of values. For example, the one that you have seen, counting how many heads I have in 3 flips of a coin. So you can only have 0, 1, 2, 3. So you have only 4 possible values. But later on, we will have another, what is called countably infinite. So infinite is actually classified into countable or not countable. And then not countable infinity can still be further classified into many kinds of infinity. The guy who more or less make a very systematic study of infinity is Cantor, C-A-N-T-O-R. George Cantor study infinity there. Now, countable infinity means basically you can enumerate the elements, so you can count them, but except that you have to keep going. So for example, the positive integers, 1, 2, 3, so you can count them. This is 1, this is 2, this is 3, but you will not be able to stop. This is, something not from this module, but the rational number can be counted too. You can actually count them by lining them up. Okay, there is some way to do so. But the irrational numbers can't be counted, so that is the contribution, at least the very first contribution from Cantor. And he devised a very general argument. I think this is worth learning, but not in this module. It's called diagonalization argument. So what he says basically is if the irrational numbers or the real numbers can be countable, then you can line them up, right? This is the first number, this is the second. And then you use decimal place expansion of the number. So now you can create a new number by going through the diagonal of this array by changing it. Then this number, the number that you construct will be different from any of the number in your list. So, but at the very beginning, you assume the real number can be listed, and so every real number will be contained in your list. But now he is able to argue by contradiction that he is able to construct another real number which does not belong to your list. So that contradiction shows that it is not countable. So it's a very clever kind of argument, and this diagonalization argument actually is being used in many occasions, not only just in logic or in number theory, but even in probability later on, not in this module though. So another kind of random variable is what we call continuous. So continuous assume one of a continuum of values. So basically you can think of it as an interval. All right, the interval may be either a finite from 0 to 1, every number there, so this is the uniform distribution or some others, or it is from minus infinity to infinity. So any real number can be possible. Your normal distribution satisfies these situations. Or from 0 to infinity, that is your exponential distribution, your waiting time. Some of you have learned chi-square distribution. The chi-square distribution takes values, non-negative values. So these are some examples. We will get into it because especially some of the distribution like chi-square, t distribution, and all this will be heavily used in hypothesis testing. So let's deal with one class of random variable. It's called discrete random variables. In fact, discrete random variable can be branched out into two. Maybe I mention it, but I think the lecture notes won't make a distinction. So this is a discrete random variable, and it has two classes. One is called nominal. The other is ordinal. Nominal means basically it's some kind of a coding. For example, you use 0, 1 to code male and then 1 as female. So it doesn't mean 0 is less than 1 in that sense. It's just a way of labeling a string, all right? Whether it's a male or female, or whether you are from a certain major. So I have 1, 2, 3, 4, 5. So it doesn't mean they are ordered. But then there are other things that are the variable 1, 2, 3, let's say, indicates a kind of a size. For example, shoe size 1, shoe size 2, shoe size 3. So they are in order. So knowing the 3, then you know 3 is bigger than 2 in a meaningful way. But whereas here, it's just a way of labeling the thing, okay? So anyway, our calculations doesn't really matter whether it is ordinal or nominal. But you have to be careful when you are dealing with nominal random variable. Adding nominal variables may not make sense, all right? Now, mathematically, it makes sense. For example, you add, so let's say this is children, and this is adult, and then these are the old people. And of course, you can attach some meaning to 0 plus 1 means any children and adult. But but it might not make sense for adding certain numbers, all right? So, okay, so this is the discrete case. And usually the discrete case for the probability mass function, we will be using a table to indicate the corresponding probabilities. So the probability mass function, we write as PMF, or probability function PF. And in a more advanced course, people actually don't even distinguish whether it's discrete or whether it's continuous. So they would call everything as probability density functions. So it is actually, if you see it, you will know what they actually mean, all right? But it is not, standardized in the terminology. So we usually use either small f, or use small p to emphasize it is a mass function. And this is the probability that the random variable is taking. So this is the quantity that we are actually computing. So how to compute this is, again, knowing that it is xi. So you go back to your original sample space, consider all the outcomes in your random experiments, which will be mapped by your random variable to xi. And then you calculate the probability over there. And we have a few notations. You either call it pi, but I think people don't quite, at least I wouldn't quite like it, because you have to tell people what your pi is standing for, which is this. So after you explain it, may as well just don't introduce an extra notation. So here we will have a f of xi, but sometimes we want to emphasize that it is coming from the random variable x, so we have a subscript, big X here, to indicate that this probability mass function is coming from the random variable x. All right, so these are just a notation, something that you need to get used to. So the collections of the pairs xi, fxi is called the probability distribution of a discrete random variable x. Now this is a formal definition here, but very often people will omit this xi here. So they would just have a bunch of fx1, fx2, and so on. And usually they think of it as a vector. And so this vector, all the entries are corresponding to the probabilities, and so they are non-negative. So the components of this particular vector is non-negative. And the thing is that when you add them all up, it is equal to 1. So this is what we call a probability distribution of the random variable. Okay. And so this is what I meant here. So f of xi is non-negative for every xi. Even xi is not a value of the random variable, but I mean we will ignore it because it is not realizable by the random variable anyway. And so this is always non-negative, and then you have to add up to 1. So to calculate the probability of a random variable, it is very so here this is our R here, all right, or the range of x. And so we have a bunch of, so we have a E here. And so this would be our x. Okay, and so the probability of x belongs to E will be just adding up all the probability. If I want to emphasize this is x. Now this is small x, so this is the notation. Big X stands for the random variable. Small x is the possible values. So, but I only add up those x that are in E itself. So here, so I won't add this in. Okay, so I'll just do this. Now this is a little bit abstract, but when we come to concrete problem, it is very clear, I suppose. But this is just giving you an overall framework, doing things in sort of like a systematic manner. Okay, I have one coin. So the experiment is flipping the coin once. So I have only two possible outcomes, either heads or either tails. And if the coin is fair, so the probability of head is 0.5, probability of tail is 0.5 as well. Now here I have a random variable, but this is just a matter of coding. If I have an edge, I call it 1. Okay. If I have a tail, I call it 0. Sooner or later we will have some other thing, because it's just a matter of how we call things a coin. For example, I am considering something like a trial. You can either have a success or failure. So you can think of heads as success and tails as failure. So we can move away from flipping the coin, but we are studying something that if I try and, for example, I'm playing a certain game, I either win or either lose. So if you win, you think of a success. And if you lose, you think of it as a failure. So then this is similar. It's the same as flipping a coin, but except that we are calling these things in a different way. But if we call it in this, then the random variable will always be 1 or 0. So 1 or 0 can be reinterpreted back according to your experiment. Whether you are flipping a coin or whether you are playing a certain game, you will win or lose. So the advantage of having the random variable is, you will see a large number of examples. Actually, the calculation is the same. Okay, whether you think of head or tail, boy or girl, success or failure, and so on and so forth, they are actually the same thing. So the probability mass function of x is f. So because we assume x is understood here, so we do not have a subscript here. So f of 0 and f of 1 both equal to 0.5. F of 1 means the probability x equal to 1, and that will be translated back to flipping a coin, I have a head. So you just do the translation back to the original experiment, and that is how you get the 0.5 here. Now, this example seems a little bit trivial, but if we proceed and then you find you have a block there, so you might go back and look at some of these simpler examples that might help. Okay, this is a Poisson random variable. For the time being, you just take it as it is. All right. The Poisson random variable actually comes from, we will deal with it, a limiting binomial distribution. All right. And it is a way to model what we call rare events. All right. We will give you the context when we come to some common distributions. But as it is now, I'm telling you that this is the probability that mass function is of this form, C times lambda k over k factorial. So what it really means is this. Is that you think of it as so this is your x, and this is fx of x. And so here the possible values are 0, 1, 2. It won't stop, all right? So it is countably infinite. So here, this is e to the power minus lambda times a constant that we do not know. We call this constant a normalization constant. All right. I will explain to you why we call it normalization, because so you will have c lambda e minus lambda, and then c lambda square e minus lambda over 2 factorial. And so a particular guy here is c lambda k e minus lambda k factorial. All right. So the requirement is that they are all non-negative. So of course, I haven't told you what C is. Actually, we are interested to determine what C is. So this is exponential function, and lambda is a positive number. So so I would have no problem to satisfy the probability mass function at any of the values are non-negative. All right. So now all I need is to make sure this is equal to. Sorry? I can't hear you. Can you? Sorry? Oh, it's too bright. Yeah. Is it better? Yeah. Oh, thank you. Oh, I never thought of doing this. So pretty dumb. I mean, yeah. So anyway, everything is involved C, so I can pull out the C here. And so I have lambda e minus lambda, and then plus, oh, okay, I would do it in a minute. So e minus lambda. Hey, I've told you the answer, actually. So according to what it is set here is C lambda. And then this is C lambda square over 2 factorial. So I don't have this. Maybe I'll start over again. I'm too excited. So this is a constant, and this is a constant times lambda, and this is a constant times the same constant over this, and then this will be, of course, so this is the pattern here. Okay, it does not stop there. So now the fact that lambda is positive, if I choose C to be positive, then everybody here will be non-negative. In fact, it's positive. So this satisfies the first condition. And then the second condition is I wanted to determine my C. So I have a C equal to 1 plus lambda squared over 2 factorial. Right? And then lambda k over k factorial. Okay, so here I need you to recall one fact, mathematical fact. This is what we call the Taylor expansion of the exponential function. So this is a Taylor series. All right, and this is just this. All right, and so if this is the case, then this sum is actually, it will be equal to e, I still have a C here, e to the power lambda. So now that I have an equation, so my C would be e to the power minus lambda. All right, so I think that is how we do that in the next slide. Okay, so this is how we do it in the next slide. So we have this is equal to 1. So C has to be chosen in such a way the entire sum is equal to 1. So this is what we call a normalization constant. So we will have this, and this follows from the Taylor expansion of e to the power lambda. So as a result, I can simplify this entire sum into one single expression, e to the power lambda. And so I just, to solve C, I divide e to the power lambda on both sides. So I have this. And now once it is done, then everything would be fine. So probability of x equal to 0. Do we switch notation? Oh, okay, I switched its notation. I call it F, but here it's called P, so it doesn't really matter what is in the name, right? So, so this is evaluate the k as 0 here. So C lambda 0 over 0 factorial. Oh, I forgot to mention one thing. 0 factorial by convention is equal to 1. The reason is factorial is how many ways of lining up the objects, right? If you have no object, there is only one way to do so. So that is just a convention, and its convention is make a lot of calculations a little bit easier, and we won't have a contradiction. So this is so I'm not dividing 0, but if I miss out the exclamation mark, then I will be in trouble. So this will be e to the power minus lambda. And then probability of x bigger than 2. There are two ways to do it, as I mentioned. One way is head-on. So what I need to do is will be add a lot of terms, x equal to 3, x equal to 4, x equal to 5, ... All right. So you have to add up an infinite sum here. So as it turns out, it is it's easier to do the opposite, because the opposite has only a few cases. Namely, the opposite is x less than or equal to 2. When x is at most 2, x can only be 0, 1, or 2. So I only have these 3 possibilities. So I plug it in, and so I will just get this answer. Okay, so this does not tell you something, but say if lambda, if we choose a lambda for a particular value, so let's say I call lambda equal to, say, 2 for this particular case. And I wanted to calculate what we wanted to do, minus P Poisson, POIS, and it is up to 2, you say up to 2 or less than 2? Okay, up to 2. So this is where your x is less than or equal to that number 2 here. And then I have to tell them that it is lambda. So I can just key in 2 here. Okay, so you will get the answer right away. All right, so this is actually the same as this for lambda equal to 2. You can verify it. So this is fairly convenient. If you are not convinced that you should throw away your calculator, everything that has calculate things, I think is a better argument here. All right. So you can do many other magic using R. All right. Okay. So let's come back here. So if a car agency sells 50% of its inventory of a certain foreign car equipped with side airbags, find a formula for the probability distribution of the number of cars with side airbags among the next 4 cars sold by the agency. So, so this is now, we are calculating it in a general situations. So first of all, decide what are all the possible values of the random variable. So the first thing is I introduce a notation first. The random variable x, big X, is the number of cars among the 4 cars sold with side airbags. All right. So this is the definition. Okay. So my big X. Now once I define my big X as this way, what are the possible values of the big X? So it would be 0 because or 1 or 2 or 3 or 4. So I will have some of the situations. Now, let me explain this term first. So if I'm saying that I will be able to sell small x number of cars with side airbags, now you have 4 cars that have been sold. Among the 4 cars, you pick X car. All right, so 4 choose X because it is equally likely here. So all you need to count is how many of them. And then the probability of the denominator is, so this is my numerator, how many such way. For example, it says the first car, the second car with side airbags. The third and the fourth isn't, all right? Or the first one, yes, the second one isn't, the third car, yes, and then the fourth car isn't. So basically 4 choose 2 is to enumerate all this possible arrangement of putting 4 things, either with 2 things that are with airbags, and then with 2 other positions without airbags. So this is how you place them. And now each of the boxes, you will have 2 choices, either with airbags or without airbags. So it's there are 2 ways of doing it. So, but now you have 4 places. You have 2 times 2 times 2 times 2. So this is 16 here. All right. Is it all right here? I mean, or I'm underestimating. Okay. So one way you can, yes or no? I mean, no. Okay. So one way you can think of it is, because I think it wasn't explained very explicitly, number of cars among the 4 cars sold has or have side airbag. All right. So so you can think of this is car 1, car 2, car 3, car 4. All right. So now how many ways that you can have 2 choices, either a car with airbag or a car without the side airbag. So you have two ways, and then you have two ways, and then you have two ways, and then you have two ways, right? So as a result, this explains the 1/16 there. All right? And now the probability that x equal to small x, it means, let's say x equal to 2. So it means that you want to, maybe I just use air, and no air, and no air. So this is one way, but then there are many other ways, right? And so on. So there are altogether 4 ways to choose 2. But here I'm thinking of general situations. So among these 4 positions, I want to have X cars that have airbag. So I have to choose X places out of these 4. So that would be 4 choose X. So this probability would be number of ways of doing it, placing which X positions where I would put the A there. And then all the possible number of ways is 2 to the power 4. So that is how this probability is done. Okay, it's better now. So this is how we can do it at one go. But of course, if this is coming a bit fast to you, depending on how intuitive you can see the problem, you can just do it slowly. X equal to 0. So now so there is only one way to do so. All the cars have to have no airbags on the side, and so there is only one way. And out of the 16 possible ways, and so you try the other one, and so on and so forth. But this is trying to tell you I have a more. I can just kill everything in one stone, all right? But you can enjoy killing one at a time, all right? So it is often helpful to look at probability distribution in graphic form. So we are telling you the histogram. One might plot the points x, f of x of a probability mass function by joining the points to the x-axis either with a dash or with a solid line. We obtain what we call a probability mass function plot, or this. So basically, why is it called a mass? You are thinking of, you are putting a metal bead at 0, at 1, at 2, at 3, at 4. And then the mass of the bead at 0 is corresponding to the probability there. So as a result, the total mass of the entire thing is always equal to 1. And to emphasize that this is only at 0, so we just have a line here. Okay, and so this is actually plotting the functions. All right. Now the blue lines is just to help us to sort of connect them, because we are basically plotting this as on a Cartesian product or Cartesian graph. So the blue line or the dashed line is trying to help us to, because if you have many of them and they are getting quite close, so sometimes you might read the wrong things. So this is one. Now the next is the more familiar histogram. So what we are doing is that this is a little bit difficult to read, so we expand this a little bit more so that the area under what we are drawing in the bar corresponds to the height. And because the base is equal to 1, so because this is the length of the base, right? Is it? And then this is the height here. So if the height corresponds back to what we have, and since the base length here is always 1, so the area is actually equal to the height. All right? So this is this. So this is just to take up more space in your plot. All right? And it gives you the idea. So it does. What it really means is using the center of 0, using the center of these rectangles as where the value is. And then the height corresponds to the probability mass function at that point. So this is this. So this is what we call a probability histogram. The rectangles are constructed so that the bases of equal width are centered at equal value of x, and their heights are equal to the corresponding probabilities given by this. So that is the thing here. The bases are constructed so as to leave no space between the rectangles. The result is what we call probability histogram. So I guess, this definition just making something very clear that already clear enough, all right? Now, if each base in the probability histogram has unit width, then the probability x equal to small x is simply the total area of the rectangle centered at x, all right? So the area and the height actually are equal. And then the total area of all the rectangles is 1, because we know the sum of the heights is equal to 1. This concept of using areas to represent probability is necessary for our consideration of the probability distribution of a continuous random variable. So, even though this is, I think many of us might prefer to have just a table in this form. Okay. A table in this form that might be helpful, then you don't need to read it. But the idea of introducing a histogram more for a visual impact, as well as for the purpose of teaching, it helps us to move into a continuous random variable. Okay, so to calculate the probability now, let's say if I wanted to find out how many cars among the 4 that are sold will have side airbags, I want it to be at least 2. What is the probability of at least 2 cars among the 4 sold have airbags? So it would mean I will add up this. It would mean that I add up this. It would mean that I would add up this area, and this area. So you are adding up the area. And this is what we are going to do in the continuous random variable. We are looking at the area specified by the statement. Okay. Now consider a group of 5 potential blood donors, A to E, of whom we know that A and B have blood type O+. 5 blood samples, they are somehow being taken, but they are being typed at random order until O+ individual is identified. So let the random variable Y be the number of typing necessary to identify an O+ individual. So find the probability function of Y. So what are the possible values of Y? So you have 3 without the O+, and then 2 with the O+, right? So usually when you try to think of what are the possible values, you think of the best scenario and the worst scenario. So this is very similar, I think, in later on as computer science students, when you analyze an algorithm, one of the things that you analyze is what is the worst scenario, worst case analysis of your algorithm. And then another would be your average case analysis of your algorithm. So, back to this example, the worst case is that somehow you have to type C, D, E first. And then, and after that, so the worst case scenario, you have to type 4 times, because the first 3 times all typing for C, D, or E, right? So this is the worst case. Now the best case is, of course, you type A or B right away, so that would be 1. So the possible values of Y are 1, 2, 3, 4, all right? And so this is, we just have to calculate this one at a time, all right? So probability of y equal to 1 means that you will be able to choose A or B first. So which is 2 out of 5, okay? And so this account 40%. And y equal to 2 means that the first one you type happen to be chosen from C, D, or E, all right? And then the second one, you have to choose either A or B. Is that all right? So the number of ways of choosing 2 people at random order would be 5 times 4, okay? And then the number of ways of having C, D, or E first, that would be 3 choices, and then followed by 2 choices where I can choose A or B. So it worked out to be 30%. So you just keep going. Y equal to 3 means you have to choose 2 out of C, D, or E first and second. And then the third one is either A or B. So, so the 5, 4, 3 in the denominator is because the first one you have 5 choices to choose. And then the second one you have 4 choices because you are not going to type the same person that you have typed. And then this is 3 because you have already typed 2. So you have altogether 5 things, so you only have 3. So this explains the denominator. How about the numerator? The first one you have to choose from C, D, or E. Okay, 3. But now the second one you also have to choose from C, D, or E except the one that you have chosen in the first choice. So you only have 2 choices here. And after that, you have to switch to choosing either A or B. Again, you have 2 choices. So this is it. So I have 20% here. Now, if you recognize that F1, F2, F3, F4 will give you the probability equal to 1 altogether, in fact, you don't need to do this. If you are confident enough that you calculate these 3 probabilities correct, then it is 1 minus these 3 numbers. Or another way is, if you want to be sure about your argument, you use the same argument and go through this calculation as it is here. And then you calculate 10%. As a double check, you can add them up, and then whether it is equal to 1. All right? So if it does not equal to 1, something is wrong. All right? So, so you have some kind of assurance. But of course, if you add them up and equal to 1, doesn't mean all your answers are correct. But that would mean at least 2 of them are not correct. So, all right? So, because you probably make mistake for at least a pair in order to somehow come up with 1, right? Or if all your answers are incorrect. So that is the worst case scenario. Okay, now so we make a table like this, or of course we can have a histogram. All right. Let me see. Maybe I'll stop here for a little while. So let's have a 5 minutes break. So let's come back at 10:55. If there is a closed form formula, just write down the closed form formula. But you have to identify what are the closed form formula applied. For example, n choose k. This is the binomial, and then you have to write. Sort like this.
Right. Okay.
And then to be extra clear would be
Otherwise,
something like this. And this is extra clear.
okay.
I just had a quick question on homework. This is question 6. It's like parallel and series.
All the
Chain.
A, B, and C, and D.
Yeah.
Okay.
So I asked you last time,
Yes.
and you said that
Oh yeah, remember.
the probability that C doesn't work
Right. So
is C.
You want C.
probability it does work.
right. So A intersect E union C intersect D works. So
Mhm.
this is the probability. Right?
And then that's C intersect all of that
Right.
over all of that,
Okay,
which we
so
already know.
so the denominator is fine.
Mhm.
So all we need is to calculate the numerator, right?
Mhm.
All right.
And you said that that would be equal to A intercept B intercept D,
Yes, I remember I told you that.
but
I
that
hope
does
it's correct.
what?
I hope. Oh, this is not entirely correct, right?
No, but what does work?
Oh yeah, because so what we do is this is B union C.
Mhm.
So we actually have to have this. B, yeah, I was too quick. So it should be B intersect C prime. So the entire thing would be probability of A. A has to work, and then
Mhm.
B has to work, but C has to fail,
Yeah.
and then D has to work.
Okay, and that's what I like. I just thought about it like in terms of words,
Yeah.
like that A works and B works and C can't work, and that's what I got. I just didn't know that those two were.
Yeah, so,
So
this
these-
is you if you argue by sentences.
Yeah, yeah.
So this come up, yeah. But,
Okay.
I can think of it this way.
And then just on question 8, it's about getting into a house, and like
Oh, so
there are 8 keys,
right.
and he randomly takes 3,
Yes.
and there's a 40% chance
Right.
the house is already unlocked.
Right.
I just before I did all this math, is it just a union of all of them?
Okay. What I would be thinking of is either the house is unlocked or locked, and then the right key is selected. Right.
Mhm.
Okay, so maybe this is can enter the house. Okay, so this is enter, right? Can't. So so this is 50-50, is it?
2/5.
2/5. So so I will have this, right?
Yeah.
And so this is no problem. So now the agent only picks 3 keys out of 8. So that means 3 out of 8
Okay.
is among the right key. So so basically.
And then you just add those two
Yeah,
up.
it's basically
Okay.
I think of it as a tree.
Okay. Is this not a correct argument? The union of all of the spaces.
Yes. Okay, this formulation is fine, but the caution as to how to calculate this, because some of them they have overlap.
Mhm.
Yeah.
So that would be like, is that not the inclusion exclusion principle?
Yes, but you will have 1, 2, 3, 4. You have 4, then you have 2 to the power 4, 16 quantities.
And then
You have to subtract things, right?
yeah. I have 15, so I must be missing one.
No, okay, you're right. 2 to the power 4 minus 1, because
Okay.
yeah, I have to choose some of the events. Right?
Okay.
Yeah.
But so this should give the same answer as that?
Okay, but you really have to be very careful in doing this. So,
Yeah.
So one way is you continue to simplify it and see whether so what is the number you get, and then verify with it.
Okay.
Yeah.
Sounds good. Thank you.
Okay, maybe I want to make an announcement, because I mean, the attendance is not what it is expected, but I suppose some of you are watching the video. But I'm not sure the students who are not here will watch the video on time. So, but anyway, this is the announcement. The midterm test has already been finalized. It is on October the 5th, Saturday. The midterm test is 1 hour. I will tell you the format a little bit more. The format that we are tentatively thinking, because I'm collaborating with the other professors in the other sections. So we will have 2 sessions. One is the multiple choice questions, and then the other is with short answers. We are still contemplating how to score the multiple choice questions. I'm the bad guy. I'm thinking of if you score it right, then I give you a certain mark. And if you score it wrong, I have a deduction. If you skip that questions, then it will not be marked. The choice of the penalty for wrong answer will be to make sure the expectation value is equal to 0. So I'm not gaining anything by deducting too much, nor I would give you too much for a correct answer, then that will encourage you to do. So if you want to play with probability, if you are able to eliminate some of the options, the more options that you can eliminate, but you can't eliminate all the other alternatives, then it might be to your advantage, depending on your luck, all right? But in the long run, if you take this module 100 times, 1,000 times, then this strategy, from a frequency approach, will work, all right? So, if you are able to eliminate some options, then you should try to flip a coin or prepare different kind of die with 2-phase, with 3-phase, 4-phase, and 5-phase die. All right. So so this is one. Now I received a lot of email because some of you. Oh, okay. Let me put it this way. You can bring in a help sheet, all right? So I recommend you to write on one side so that you can recycle them, because in the final exam, you will also be allowed only to bring in one A4 size paper. But it's up to you. You can write on both sides, and then if you are preparing for the exam, then you have to start afresh again. But it is really your personal choice. You can bring in your calculator. I think it's a closed book, so you can't bring your laptop in. You can bring your laptop in, but not on your table. All right. So please be there earlier. At least allow yourself 15 minutes early, because we actually will probably let you in, say 10 minutes before or 5 minutes before. We are talking about something like close to 500 students. So later on, we will upload a seating plan for you. So you have to familiarize yourself where you go to. The place where we are having the exam is in the sports hall. So put on your sporting gear, all right? So it would be Hall M1, not the phone company. Hall M1, I think it's on the first floor of the multi-purpose sports hall. Okay, the following announcement concerns with quite a number of you taking some other modules, something like PC something. And it happens that the midterm test is also scheduled either overlap with our test a bit or a back-to-back. Now, I received email, some poor guys have 3 midterm tests scheduled on that same day. I checked with the NUS policy. NUS has no policies on the midterm test, but I think they have policies on final exam. But when they arrange the timetable for the final exam, they will take care, possibly this thing won't happen. You are not supposed to take more than 2 exams within 24 hours. That only applies to exam. But since they are, so they would let us do whatever we want for midterm tests. Because multiple choice question is very difficult to set. It's easy to grade because we are going to use machine to grade it. But setting it, so what it means is that we will probably not budge to, if there is an overlap, we'll try to arrange you to take the test slightly earlier so that you will be able to go to the other test. But if it's a back-to-back, probably we will still allow you maybe 10 minutes or 15 minutes earlier so that you have a bit of time to go to the exam hall for the next one. But for some of these unfortunate guys, if you have 3 tests or 4 tests or 5, I can't help you, all right? So, so this is unfortunate. Or fortunate, you kill all your tests in one day, right? But don't kill yourself. So anyway, okay. I think it's okay for me if you use pencil to answer your questions, especially for session B, for short questions. You don't need to use ball pen to do so. For calculator, I think you can bring in any calculator you want. I mean, programmable calculator, whatever. But you will see the calculations are pretty easy. Yes.
So will we actually be doing combinatorials and all of that?
I would think so. Okay. Oh yeah. What will the test cover? Yeah, I mean, I forgot what I talked to the other person. I know some of the students use tutorial as a way to cut off the things, but I think this is too exam-oriented. I would use by a certain, say, sections of my lecture notes, which will sync with the other lectures sessions. That would be this. And I will try to upload the week 7, that is the week after you take, that is the week immediately after the Saturday you take the test. So, so that at least you get to know if there is some material that is part of the test curriculum, then you can practice your work there earlier. Okay. Any other questions? Yes. Okay, it would be 10 to 11. We will possibly, okay, I mean, the local students probably are very used to this. You are only allowed to come in if you are not too late. And then towards the end of the test, I think maybe 10 minutes or 15 minutes, you can't leave. I mean, there is this kind of rule in NUS. But probably, since it's a midterm test, it is recorded here, but I think it's no harm. I won't be jailed. So, anyway, so because the midterm test is entirely, monitored or administered by us, so we don't need to follow 100% the protocol that NUS is doing. But in the final exam, we are also invigilated by the registrar office, so we have to, do it in a very, very formal way. All right. One more announcement about the test. If you are not able, if you are sick, on whatever day you are, but you have to have an MC to cover that particular day. Suppose you are sick on Thursday, but you are well. The doctor is only able to give you the MC for Thursday and Friday. You really have to back him or drink a lot of hot water, so that you look like you are having fever, then asking him for Saturday MC as well. So you need MC. Now, another thing is if you are on a certain trip that you are traveling, if you are traveling on your own or for National Geographic or BBC travel, then we probably won't budge, all right? So, but if you are if you have to be away because you are representing NUS for some sports competitions or for the national level, then we probably can consider. So you need to have very good excuse for missing the test, all right? If you are not sick and you have to miss it. Okay, so some of the things we can consider case by case, but because I wanted to set some policy so that the whole idea is it would be fair to everyone. And okay. So another view of probability function. It is often useful to think of a probability function as specifying a mathematical model for discrete populations. So we have a population in mind, and we are looking at certain way of this population, depending on what we are interested. Okay, so this is this. Consider selecting at random a student who is among 35,000 registered students for the current semester at NUS. So NUS has about 35,000 students, and let X be the number of modules for which the selected student is registered, for which the selected student has registered, and suppose X has the probability density function, probability mass function in this way. So this is fairly reasonable numbers. Okay, I don't know whether it's unlikely it is based on hard, data, but probably it's a fairly good guess. So the majority of the students, about 40% of them, take 5 modules in a semester, and then very few take one module. Probably these students wanted to wrap up their study here, and then there are some students who are very ambitious and taking 7 modules in one semester. Okay, so this is what we call, later on, we'll call this is the mode. 5 is the mode of the distribution because this corresponds to be the highest probability. All right, we will not probably talk about this. Okay, so one way to view this situation is to think of the population as consisting of individuals. All right, and then each having his own or her own X value. X value means the number of modules that he or she is taking, and the proportion with which X value is given by this. So if I randomly pick someone with 13% of chance, I will get a student taking 3 modules for that particular semester. But there is another view. Another view is simply change the student from a person to a number. All right. So an alternative viewpoint is to forget about the students and think of the population itself as consisting of the values 1, 2, 3, up to 7. So you can think of it as a bag. There are a number of ones. So for example, I will have 1% of this. So I will have 350 in the back. I have 350 ones in the back. All right. Okay. 1% of this, right? So it is 350. So so I have. You can think of it as tickets. Okay, 350 tickets with 1 on the top of the tickets. So I'm not thinking in terms of the person, but in terms of things that characterize this student by a number. So I'm thinking of a bunch of 1s, 350 of them, and then a bunch of 2s, and a bunch of 3, and a bunch of 7s. And so that should be, since 7 would represent 2% of the students taking 7 modules. So I will have 750 such tickets with a 7 on it. So majority of the tickets are labeled as 5, and some are and then the second majority would be either 4 or either 6, and so on and so forth. So this is just a different views, all right? The population then consists of the numbers 1, 2, or 7. And f of x gives a model for the distribution of the population values. So once we have such a mathematical model for a population, we will use it to compute values of the population characteristics, such as the mean. So this is just paving the way of why we are defining the expectation or the mean of a population in this manner. Okay, we will come back to it, I think, when we get into expectations. I think 2 or 3 sections down. So now we change gear to continuous random variable. Now, later on, we will come back to the discrete one for what we call the cumulative distribution function. We are not interested in individual probability, but we are interested in the cumulative probability up to a certain point there. So later on, we will, the section after this will be about the cumulative distribution function. And then here we usually call CDF, all right? But we'll move to the continuous random variable first. So there are many natural random variables whose set of possible values is uncountable, all right? For example, the random variable x, which denotes the lifetime of an electrical appliance. So it can be any number from 0 to infinity. Or a random variable y, which denotes the amount of rainfall we get in a month, all right? So from 0 to any reasonable large number. So a continuous random variable is one that can assume any values within an interval, all right? Or a collection of intervals. We probably won't see these situations, all right? So this is more like a mathematical possibility, but the kind of random variable that we deal with are usually just one single interval. But sometimes it can be unbounded from 0 to infinity, or it is bounded between A and B, all right? So for example, height, length, speed of a car, the amount of alcohol in a person's blood, the tensile strength of a new alloy. So these are all continuous random variable, or time for certain work. For example, one of the things that people compare algorithms is comparing the time to execute the same job by different algorithms as a way to see which algorithm is better. So in this case, the probability mass function is not applicable, all right? And instead, we characterize the probability distribution of a continuous random variable by this type of interval, okay? Strictly bigger than A, less than or equal to B for any interval AB. Now, the same question actually can be asked for a discrete random variable, but we can have a change from discrete random variable, whether we use the probability mass function or use this. But the approach for continuous random variable, we use this, all right? We are not talking about single probability that x equal to a particular number. That would be 0. You will see it soon. So we say that x is a continuous random variable if there exists a non-negative function f to remind us that it is coming from the random variable x. We have a subscript here, x here, to remind us that it is associated with this random variable x. Defined for all real x, all right? Having the property that for any interval AB, this probability of interest is actually given by an integration, integrating over the interval AB, which is defined by this, all right, by your problem. And then the integrand is a special function, and that special function is what we call a probability mass, a probability density function of the random variable x. It probably doesn't really matter much, but one thing I want to emphasize is because of the way it is introduced, density function may not be unique, all right? In fact, I can always change a little bit on the density functions because the defining property of this density function is that it has to satisfy the probability here. So if I'm just being naughty to change a little bit individual value, only a few of them, the integration will still be the same, because we are talking about the area under this small f. So if I make a little change of only selected value, the area won't be changed. All right. So so sometimes people try to avoid using the article here because you may not have only one. All right. So you can have more than one. Okay. And if x is a continuous random variable, probability of x equal to small x is equal to 0 for any x. So this is the point that I make somewhere quite earlier in this module, is that this is not empty set. Okay, this does not mean it is an empty set, because for continuous random variable, this may happen. All right, but this happens with probability 0. All right. Okay. Okay. So so this must not mean it is an empty set here. So and also similar reasoning is for probability of x equal to b. So what it means is now whether you think of excluding a and excluding b, or excluding a but include b, and two other possibilities, it doesn't really hurt. It will give you the same number. All right. So you don't need to pay attention to whether this is strictly less than or equal to. Similarly for this inequality. So all of this will be given by this integration here. All right. Now this is in a stark contrast with discrete thing, because if the discrete random variable here and this will differ by the probability of x equal to b. And if probability of x equal to b is something positive, this probability would be bigger than this one. All right. Okay. So okay. And this is represented by this. So so whether you have equal signs in one of them doesn't really matter. So this is the area under the curve. Okay. And this is very similar to the histogram that I was trying to relate to, the histogram with base width equal to 1, and you're adding up the area of the rectangles. So now we just think of the rectangle are so small that you have to add up. When you add them up, it would give you back this area of the curve here. Now, there is an advantage of this, because it means that calculus, we can have a very powerful tool of calculus on our side to do the calculations. All right. So here, this is the point here. Probability of A equal to 0 does not necessarily imply that A equal to empty set. The other way is right. If A equal to an empty set, it implies probability of A equal to 0. So, so this is just saying that the implication is only from A equal to empty set imply the probability equals 0, but you do not imply it back. X assumes value only in some interval a, b. We may simply set f of x equal to 0 when it is outside. So meaning that it's the density. Now, if you have physics background, you can think of this is a wire, all right? So a wire that is of not uniform length, and then you wanted to find out the mass of the, so this function is just giving you the density of the wire along the wire. And to find out the mass of the wire from this endpoint to this endpoint, you just simply integrate the linear density of the wire, right? So this is the interpretation here. So the area, if you're thinking of a wire that is not necessarily of uniform density, which is given by this, then the probability is corresponding to that chunk of the wire, is the mass of that wire. Okay, So properties of a probability density function. Now, sometimes we have, I think there is a subtlety here in the definition. Earlier, we have a random variable in mind first, and then it would definitely have what we have. But here it is now our standpoint is I have an arbitrary function. If the arbitrary function satisfies these two properties, we know it would correspond to a certain random variable, and the random variable has a density function given by this. Okay, so now we have no random variable as our background, so we insist that the function has to be non-negative because it corresponds to the probability density function, and then the total area under the curve will be equal to 1. All right. Okay, any function here that satisfies the above two conditions at the same time will be or can be a density function of a certain random variable. Okay, so this is just a numerical example. Someone told you I have a candidate function f of x, which is basically the main thing is this term, x squared times 1 minus x. But I'm not sure about how to adjust this, all right? So let me just call it a constant k, all right? Now, since x is between this interval, 0, 1, x squared times 1 minus x would be non-negative. So in order for f of x to be non-negative over the entire real number, k has to be non-negative, okay? But I have another condition. The entire area under the curve has to be equal to 1. So as a result, I can pin down what k is because I'm going to do integration over this interval, 0, 1. And so I will be able to compute the integral of this over 0, 1. And so I will have a number there. And then this number will times this k. And so as a result, and I insist it has to be equal to 1. So I will be able to solve k. So this is how it goes. So this is the defining property, condition B of a density function. And so I can ignore the integration from minus infinity to 0 because the density function is 0. So it would not contribute to the integral. And also from 1 to infinity, it will also not contribute to the integral, right? Because you look at the, so anything outside 0, 1. So as a result, we only need to concentrate on integrating the function from 0 to 1. But when I'm integrating from 0 to 1, f of x is taking this form, okay? Now, suppose f of x takes different form over different interval. Then you have to pick the right form for the right interval. Okay, anyway, so the integration is kind of straightforward. So, and it turned out to be 1 over 12. So that would, in order for it to satisfy equal to 1, so I must have k equal to 12. Now, computing probabilities. This is something like what we call exponential distribution. Exponential distribution is usually used to model, say, the lifetime of an electrical appliance, provided that, there is no memory property. If you are coming from engineering school, a step forward to modify the exponential distribution will be the Weibull distribution. So the Weibull distribution is a way to rectify certain deficiency of the exponential distribution in terms of basically they want to model the fatigue of a component. If the component has been running for a longer time, the idea is that the component is aging, so it is more likely to fail. Okay, so over there. But now, okay, so probability of x in between this. So it's basically integrations, and so this would be just straightforward. Is that okay? That's okay, right? I'm integrating exponential function. Okay, so it's okay, right? I assume, integrating exponential functions are easy. Okay. So the example 3 is basically a mathematical example. Without giving you the background of the thing, but here, this is here. Time headway in a traffic flow control is something that we want to measure. So it's the time between one car and the next car passing through a fixed point. So basically, they wanted to control the gap there, all right? And so this is one of the probability density function was suggested. And so you have to watch out. X is not starting from 0, but X is starting from 0.5. So possibly they don't want it to be, really bumper-to-bumper kind of movement. Okay, so this is just basically this. So the first thing is we want to verify that this is a probability density function. So the first thing is this sentence is needed, all right? Even though it might be obvious, but in exam or in whatever things, this is one of the things we are looking for. It has to be non-negative. And then the next thing to verify it is a probability. So this is condition 1. And then condition 2 will be the integral over the whole real line is equal to 1. Okay? So we need to verify this. And so in between is just integrations. All right? Now the integration here is done in this way, but then there is a slightly alternative way of doing it. One way is use a change of variable. Put y equal to x minus 0.5. Okay, and then it would be, then you can change the lower limit of the integration to 0 after you have moved it by 0.5. So I guess it might be easier to do the calculations if you wanted to. So maybe I'll just indicate my point here. So this is just an alternative. So I'm integrating r fx of x dx. But of course, this is and so if I have a variable of integrate, this is my substitution variable. So it would be changed to this. Okay, and then this is equal to y. Because in general, you have this. As long as this lambda match this and you're integrating this, this will be equal to 1. All right? So, so this is just an alternative way rather than handle the little corrections, 0.5 there. But it's not a big deal here. So, yes?
So for the, I mean, what you was the slide, when it says that f of x is greater than 0 for all x, we
right.
just have to say it, we don't have to give a reason?
In this case, you can say that it's pretty obvious because this otherwise is okay. But over this range, because exponential function is non-negative. Yeah. So, yeah, I think this is, there is a call of judgment here, how much you have to explain. It is very difficult because it depends on your audience. So one way I think you just treat all of us to be your peer. If you can, those information or those facts that you already know, you assume I also know, so you just help me to recall that particular fact. But if you, overestimate us, oh, you know everything, then I don't even need to answer. I don't even need to explain anything. Then, yeah. Or I assume my professor is really dumb. I start from additions then it will take a long time to arrive at. So there is an art here, how much you have to explain, but depending on who they are. Okay, so here, I think the careful thing you have to watch out is when it is the f of x has two expressions. That's the most important thing. F of x has two expressions, and depending on where you are, the function will take on one particular expression, and then the function will take on the other expressions. So here, from minus infinity to 0.5 would be the function will take on the expression 0. So basically, I don't need to concern about it, and then I only have it here. All right. So you can have this, or another way is just similar to what I did is move it by y equal to x minus 0.5. So your integration would be from 0 to 4.5, and so it might be easier to deal with rather than. So it is really a matter of preference. All right. So it worked out to be something like almost like 50%. Okay. So maybe I stop here because I think I probably won't be able to do much. But the cumulative distribution function for the continuous random variable is just this. But now for the discrete random variable, we have to be careful. So this is what. Can you give me a minute? So what we are going to do will be from either a probability density functions or probability mass function. We know how to calculate the CDF, cumulative. And now what we are going to do is to do it the other way around later on. If I know the cumulative distribution function, I wanted to calculate this. To calculate this, I differentiate. And to calculate this, I use subtraction in an appropriate manner. All right. So as I mentioned, differentiation and subtractions are actually parallel. All right. So, okay. So I'll stop here.